In this video, we'll go over the basics of CMOS single-stage operational amplifiers with a focus on the folded-cascode amplifier. Now, as you know, when we think of an ideal op-amp circuit, we think of a circuit with a high gain and a low output impedance. However, it's difficult to combine both of these facets in a single stage in a CMOS technology. So therefore, single-stage op-amp circuits in CMOS are usually realized as operational transconductance amplifiers. These are so named because they can provide a large gain at DC from a single stage by combining a transconductance, labeled GMA here, with a large output resistance, Rout. So this is naturally a good fit with CMOS technology where the transistors have a small signal transconductance and can have a relatively large output resistance when configured in the common source configuration. Now these single-stage amplifiers having a high output impedance are suitable for driving the mostly capacitive loads that are usually encountered in CMOS integrated circuits. That is, when the amplifiers are driving at their output, the gate of another CMOS stage presents mostly capacitive load, and so the combination of GM and large Rout provides a high DC gain. However, they don't provide the other aspect that we expect from op-amps, which is a low output resistance. Fortunately, we've already seen how feedback can help to reduce the output resistance of op-amp circuits. So with feedback, single-stage operational transconductance amplifiers, also called OTAs, can also be used to drive some resistive load. Now the primary parameters of our first-order amplifier model were the DC gain and the pole frequency, the single pole frequency. So in the case of an OTA driving a capacitive load, we've got a small signal model for the OTA's open loop response as shown here. The DC gain is simply given by the product of GMA and the output resistance because the capacitors look like an open circuit at DC. It's a first order frequency response with a single pole that arises due to the RC time constant at the output. That is, it's 1 over the product Rout and the parallel combination of Cout and CL. So that's the single pole frequency here. So given the DC gain and the single pole frequency for the first order model, we can arrive at the unity gain frequency of the amplifier on its own. This is denoted with the symbol omega with a subscript TA. The A reminds us that this is the unity gain frequency of the amplifier on its own, and is therefore not necessarily the same as omega t, which is the unity gain frequency of L, the loop, including the feedback network. In any case, the unity gain frequency of this first order amplifier is the product of the DC gain AV, defined up here, and the pole frequency. So since Rout appears in the DC gain and also in the denominator of the pole frequency, it cancels and you end up with a unity gain frequency. That's a relatively simple expression here. It's the transconductance of the OTA divided by the capacitive load it's driving. Now, one of, if not the most common example of a CMOS single-stage OTA circuit is the folded-cascode. So an example folded-cascode op-amp is pictured here with the input pair Q1, Q2, and driving into the folded cascode transistors Q5 and Q6, and then an active load, active cascode load, current mirror load down here. Strictly speaking, because of the active load current mirror down here, this circuit is not perfectly symmetric, but if we could think of a sort of equivalent half circuit here, clearly it would be a folded cascode formed by Q1 and Q6 driving the output node here. So relating it to the first order model of the amplifier we showed on the last slide, the transconductance of this stage, GMA, is just given by the small signal transconductance of the input pair transistors, Q1 and Q2. On the other hand, the output resistance is seen looking into the output. A small signal analysis would reveal that it's a parallel combination of the resistance looking up into the drain of Q6, which is cascode style output resistance, relatively large, proportional to GM times RDS squared. Likewise, looking down into the cascode combination of Q8 and Q10, again, you see a large output resistance that's equal to a GM times an RDS squared with some multiplicative constants in there. So you've got it's a prototypical OTA with transconductance driving a large small signal output resistance. Some other details on the schematic. The transistors Q12 and Q13 are additional transistors that are added to improve slew rate performance. The amplifier, will discuss them later, but they can be ignored for the time being. Under normal small signal operation, they would be turned off at all times. And another important point to note here is that in order to allow for a relatively large voltage swing at the output, we would need additional circuits, not shown here, to produce the bias voltages for the cascode transistors, VB1 and VB2. If a wide swing cascode biasing circuit were used, then that will allow a larger swing at the output node, VO. Now, clearly this schematic, if we did a rigorous small signal analysis of the whole thing, we would see many poles and even zeros. But fortunately, some simplification is possible. So if you take a careful look and you go node by node through this circuit, you'll find that the small signal time constants associated with the capacitances to ground at each and every node in the circuit includes a term proportional to 1 over GM of some transistor, small signal transconductance of some transistor in the circuit, with the exception of just one node. So for example, if we look at it, if we consider this node, then we'll have some capacitance to ground, but the small signal analysis will also reveal that we have a small signal resistance of 1 over GM5 to the small signal grounded gate here. Similarly, if we consider this node, we see the 1 over GM of Q6. If we consider this node, we see the diode connected Q9, which has a small signal resistance looking down here of 1 over GM9. So as a result, all the time constants are relatively small, and the associated poles will be at much higher frequency, except for the one dominant pole which arises at the output node. The output node is the only node by design of the circuit that has a very high output resistance, and we need that high small signal output resistance to provide us our large DC gain. At the same time, it's quite likely that there's a relatively large, if not very large, load capacitance connected at the output node. So it's most likely that the output pole, the pole associated with the output node small signal time constant, will be dominant, will be at a much lower frequency than any other pole in the circuit. As a result, a first order model is quite appropriate here. Here's the result of the first order approximation. You've got the DC gain in the numerator, which is GM1 times R out being the overall output resistance of the whole thing. And GM1, of course, being the small signal transconductance of the input pair transistors. The single pole arises at the 1 over the output time constant. So we've got this term S R out CL in the denominator here. Now, putting these together, we saw already how the unity gain frequency of first order amplifier we expect to be GMA over the load capacitance. And so in this case, the transconductance of the amplifier is GM1. So the unity gain frequency of the single stage amplifier is just GM1 over CL. Now, if we put this in a feedback loop with feedback factor beta, that means that the unity gain frequency with the first order model of the whole loop will just be beta times the unity gain frequency of the amplifier, beta times GM1 over CL. So when it comes to designing this folded cascode amplifier, we can already draw some simple conclusions from this first order analysis. First of all, for fixed load capacitance CL, in order to increase the bandwidth of the closed loop amplifier, omega T, we've got to increase GM1, right? Because if CL, the load cap, is fixed, beta is determined by the desired gain of the closed loop configuration. So really, it's only GM1 as designers we can control. In order to do that, we would have to increase the tail current here, I bias 2, which sets the bias current through Q1 and Q2. And or we would size, that is, select the W/L ratio of Q1 and Q2 in such a way that the input pair is operated with a low value of V effective. Again, for a given drain current, that's going to maximize the small signal transconductance in those transistors, and hence the unity gain frequency and the closed loop bandwidth. Likewise, similarly, to minimize the power consumption for a fixed bandwidth, we want to maximize GM1. Now, to do that, we would want to actually decrease the tail current. The power consumption is obviously proportional to the amount of current that we're drawing from the power supply. But at the same time, we would still wish to operate the input pair with a very low value for V effective of transistors Q1 and Q2, because again, that's going to give us the most bang for the buck. That'll allow us to get our needed GM with the lowest possible current consumption. So we see that in any case, whether we're trying to maximize bandwidth or minimize power consumption, in either case, it seems to be in our interests to bias this input diff pair with a low value of V effective. So we've already talked about how once these transistors approach subthreshold operation, you kind of get diminishing returns for reducing V effective even further. And instead, what you just see is an explosive increase in the size of these transistors. So a typical choice is to operate these transistors sort of on the verge of subthreshold operation. Although in some cases, for extremely low power applications, you'll see them actually biased all the way in subthreshold operation. Classic example there is in digital wristwatches, where you need the circuit to operate from a very low, a very small battery for a very long period of time. Then you'll see circuits operated with very low, where the input pair is operated with a very low V effective. So here we have a summary of what we've just been talking about. Over here on the left, we have the schematic of the folded cascode single stage op-amp, and on the right, its small signal equivalent circuit, highlighting the transconductance capital GMA of the op-amp, which we've said is equal to the small signal transconductance of the input differential pair transistors Q1 and Q2. Now, if we're biased in a square law regime, then we know that that small signal transconductance is equal to 2 ID over V effective. Now in this case, 2 ID in fact equals I bias 2. So making that substitution and recognizing that the transconductance of the OTA is equal to GM1, we've got a relatively simple expression shown here for the transconductance of the OTA, assuming that the input diff pair transistors are observing a square law. And we've already said that there's every incentive, therefore, to bias those transistors with a low V effective, giving us the largest transconductance for a fixed bias current I bias 2. And doing so ultimately in the limit puts us into subthreshold operation. So when we reach subthreshold in the denominator, instead of seeing V effective 1 and 2, instead we see the thermal voltage showing up here. So that's sort of a limiting case. We can't get ever higher transconductance just by lowering V effective all the way close to 0. Instead, we reach a point of diminishing returns as the transconductance approaches the value predicted by the subthreshold equation. And that's why we may often see that those diff pair transistors biased sort of on the verge of subthreshold operation. The output resistance, small signal output resistance, the cascode stage is on the order of small signal GM times RDS squared. And that's because at the output node, we see a cascode stage looking up and a cascode stage looking down. And then here are the expressions for the amplifier's frequency response, which can be also written in terms of its unity gain frequency omega TA, which is just GM1 over CL. So that was our simple first order model of the folded cascode OTA. And we've said that in order to increase the bandwidth, we would increase GM1 and 2 of the input diff pair transistors, and for a fixed load that would increase omega TA and thereby increase the closed loop bandwidth of the amplifier. But again, that's according to a first order model. In reality, the circuit's obviously quite complex, and there are several other poles arising. And these can be estimated from the time constants associated with various nodes in the circuit. So in reality, we can't increase omega T indefinitely, because at some point as it approaches the equivalent second pole of this amplifier, our the closed loop amplifier's phase margin will degrade and we'll start seeing some undesirable dynamic behavior. So remember that ultimately we will be limited in increasing omega T by the location of the second pole frequency and the required phase margin. So there's a couple of candidates for time constants that may predominantly give rise to the second pole in this amplifier. One is the time, one candidate is the time constant associated with these nodes here. These nodes here look fairly similar, and they both have similarly sized transistors connected to it, Q5, Q4, and Q13 in the case of this node here, and Q6, Q3, and Q12 in the case of this node here. So we've probably got comparable parasitic capacitances to ground associated with both nodes. And in both cases, we're looking into the source of a common gate transistor. Now, there will be subtle differences in the small signal resistance seen in each case, but anyway, in both cases, we've got um, CGSs associated with this node, and so some decent sized parasitic capacitors, but a relatively small signal resistance that's proportional to 1 over GM of these transistors. The other candidate for the second equivalent pole is the time constant associated with this node. Here we've got capacitance due to the CGS, gate source capacitance of these two transistors, Q9 and Q10, as well as the drain to body capacitances of Q7, Q8, Q5, and Q6. So again, a fair number of parasitics capacitances associated with this node, and 1 over GM small signal resistance, 1 over GM 9 in this case. So, although clearly it depends on the precise details of the sizing of the various transistors here, if I had to guess, I would say it's more likely to be this node here. So interestingly, here we've got a second pole that, if we assume it's roughly equal to 1 over the time constant associated with those nodes, we might estimate it at GM over the total capacitance to ground of this node, which includes the CGS of transistor Q5. There are other capacitance as well, but that's sort of a lower limit on the capacitance associated with this node. And so therefore it provides an upper limit to where this second pole frequency associated with that node may be. And so written in this form, we see that omega P2 is upper bounded by GM5 over CGS5, which we've already seen is actually the unity gain frequency of transistor Q5. So if we're interested in increasing the bandwidth of this amplifier, and we're going to be compensating it to have a specified phase margin, if this is the equivalent second pole, it means that our compensation will ultimately be limited by the FT of this transistor here, Q5, and its sort of matched transistor Q6, of course. So in order to increase the equivalent second pole at this nodes, we need to choose the bias point for these transistors according to the criteria that we would use to maximize their FT. So specifically, we would seek to minimize their gate length, the gate lengths of Q5 and Q6, and we would also seek to bias it with relatively large V effective. The reason being for fixed bias drain current, larger V effective will mean a smaller transistor with therefore smaller associated parasitics. So um, that's not too surprising. And so having done everything we can to maximize that second pole frequency, then what we do is just um, compensate the loop to achieve the specified phase margin without impacting that second pole. The pole associated with this node here, although it also has similar parasitic capacitances associated with it, also associated with CGSs, um, in this case, the 1 over GM is that of the NMOS transistor Q9, whereas the time constant at this node is determined by the 1 over GM of a PMOS transistor. And since often the electron mobility is higher than the hole mobility, given that these are biased with the same drain current, we may expect that GM5 is greater than GM9, and therefore that GM5 is lower than GM9, and that therefore this pole is, that the pole associated with this node is most likely to be a lower frequency. So if we use the folded cascode OTA in a closed loop feedback amplifier, and we find that the phase margin of the folded cascode op-amp on its own is insufficient, because let's say the dominant pole at the output is not far enough below the second pole associated with, let's say, this node, then what would we do? Well, the first thing we can do is perform dominant pole compensation. To do so, we would reduce the amplifier's 3 dB bandwidth by adding additional output capacitance. Doing so would in turn lower the unity gain frequency of the op-amp, omega TA, and that in turn, assuming feedback factor beta is constant, would lower omega t being equal to beta times GM1 over CL. So increasing CL is the first thing we do. That would give us dominant pole compensation. We can also seek to improve the phase margin by increasing the bias current in these two branches here. Doing so increases the current, the bias current of these two transistors, ID5 and ID6, thereby increasing their small signal transconductance, and thereby increasing the poles, the second poles associated with these nodes here, and that will also give us extra phase margin. Finally, the last thing we can do is introduce some lead compensation by adding an additional resistance RC in series with CL. It can be shown that doing so introduces the lead compensating left half plane 0 at a frequency determined by 1 over the time constant RC and CL. Now, it may not always be possible to introduce this resistance, but if it is, then it can buy you an extra 15, 20, maybe even 30 degrees of phase margin without significantly impacting the unity gain frequency of the loop, and thereby the 3 dB frequency of the closed loop amplifier. So here's a simple but important example where we consider the settling time of a switch capacitor circuit. So the schematic shown here is representative of the single-ended equivalent of a switch capacitor circuit in one phase of its operation. Even if you're not familiar with switch capacitor circuits yet, you can just imagine that it's a negative feedback loop with a capacitive voltage divider for the feedback network, and there are switches that are applying transient step voltages to this circuit and periodically resetting them. So we're very, very interested in how long it takes for the output of this op-amp to settle when a transient step is applied over here. Now, given that if we adopt a first order model for our OTA here, then we've already talked about how the closed loop amplifiers, 3 dB bandwidth, and single time constant settling time tau are dependent on the unity gain frequency of the loop L. So we can analyze the loop response L by breaking the loop here. And doing so gives rise to the circuit shown on the right, where we've simply got the single stage OTA here, whose frequency response can be modeled at frequencies around its unity gain frequency by this simple expression here. That's our integrator model for uh, a first order op-amp, single stage op-amp. And then the rest of the loop is simply this capacitive feedback network that forms a passive voltage divider with a gain from here to here of C2 over C1 plus C2. So the loop gain L is therefore given by this expression here. We've got the amplifier response, the integrator model for it, followed by beta, the capacitive feedback network. Now we can easily solve for the frequency, substituting in S equals j omega here and solving for the frequency omega t at which the magnitude of L is equal to unity gives rise to, we can easily solve for omega t, resulting in this expression shown here. Omega t is just equal to the amplifier's unity gain frequency omega ta times the feedback factor beta over here. And this in turn is also therefore the expression for the 3 dB bandwidth of a closed loop amplifier, and therefore the settling time here is just 1 over this expression. Now here's a simple example that illustrates how even the analysis of a very simple feedback circuit can trip people up sometimes if they're not careful about applying the principles of feedback properly. So let's say you're faced with the same capacitive feedback inverting configuration shown here, and you wish to estimate the pole of this simple circuit, assuming the op-amp has a large DC gain and the op-amp itself has an output impedance RO. Let's say, for example, this is the Folded-Cascode OTA, and therefore RO is quite large. One might be tempted to look at the circuit and say, oh, okay, well, over here at the negative op-amp terminal, I've got a virtual ground. So therefore, this node here is pretty much at 0 volts all the time. So I've got a simple first order single time constant response at the output, which is the dominant pole of this network. And that single time constant is formed by RO and the feedback capacitor C2, which is connected between this node and my virtual ground. So the circuit, therefore, we might conclude, has a pole at the frequency 1 over RO C2, right? And in fact, that's dead wrong. And there's just a basic fallacy here in the analysis. Now, the analysis is more properly done by using a first order model of the op-amp and substituting it into the schematic. Moreover, we can set the independent source at the input to 0, that is, shorting its ground, and we end up with a simple first order network, feedback network that can be analyzed. So in this case, we can break the loop here. We've assumed that the op-amp input impedance is very high compared to the other impedances connected to this node. And so then, therefore, the analysis is pretty simple. If we apply a test voltage on this side of the break, then over here we've simply got GM times the test source and that's driving a combination of RO and the voltage divider C2 over C1 plus C2. So, so rigorous analysis is performed here for the loop gain, the resulting loop gain L. It's just some algebra that you can follow through, and then we can find the pole of the closed loop amplifier, which is what's going to tell us about our settling time by solving, finding the roots of the denominator of the closed loop response. And that is, since the denominator of the closed loop response is 1 plus L, we need to solve for the roots of 1 plus L equals 0. Substituting our expression for L in here and rearranging to solve for S, we get the expression shown here. So this is still a fairly complex expression, but um, you know, it's a very reasonable approximation to assume that the OTA itself has a relatively large DC gain. That is, that the product of GM and R out is much greater than 1. If that's not the case, we really don't have not much of an op-amp at all here. So this is certainly a pretty reasonable approximation to make. And having done so, we can now neglect these two terms here. And we then get a relatively simple expression where we can cancel RO, numerator and denominator, cancel C2 in the numerator and denominator. We solved for the roots here, and we got obviously a left half plane 0. That's what the minus sign tells us. So that's good because we always generally assume that L on its own is stable, and the frequency of the pole of L, or sorry, the pole of the closed loop amplifier is given by GM over C1, interestingly. So in fact, remember, it's very different than what we got using the erroneous assumptions on the last slide, where we thought, well, maybe the pole of the closed loop amplifier is 1 over RO times C2. In fact, it doesn't depend on C2 or RO at all. It depends on the transconductance, GM, of the op-amp. Higher GM will give us a faster settling time and a higher 3 dB bandwidth. And it also depends, in fact, on the capacitor C1 instead of C2, which is a little bit surprising. So our time constant is 1 over omega t for this first order model, C1 over GM.